Hi friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 658. Find key closest elements. In this video, we are going to share three solution formats. The first one is based on defining sorting key. The second one is sliding window. And the third one is binary search. So first, I'll read through the statement to digest the task, and then we do some detailed analysis, and finally we share all the codes. First, let's look at the statement. So given a sorted integer array called array, and two integers k and x, return the k closest integers to x in the array. So the result should also be sorted in ascending order. So next, the problem defines an integer a is closer to x than an integer b. So if its absolute distance from x is smaller than that of b, or if they are the same, so if a is less than b. So this is the main statement of the problem. Now let's look at the two examples. So in example 2, so the x is very small, it's -1. It's smaller than the first element, in other words, the minimum of the array. So we just need to return the first four elements according to the problem statement. So this is actually a very simple case. So in the first example, so there are two length 4 segments. So as the array is sorted in ascending order, so the k elements to be returned must be consecutive, right? So here we should return either 1, 2, 3, 4 or 2, 3, 4, 5. Actually, their distance sum to x is the same, but due to this second assumption or requirement in the closeness, so we should return 1, 2, 3, 4 rather than 2, 3, 4, 5. So this is the example 1. So now, before we analyze the problem, let's also look at the additional constraints or assumptions. First, the length of the array is bounded above by 10 to the power 4, and k is less than or equal to the length, right? So array is sorted in ascending order. So the last one is on the range of elements in the array and x. So with that said, we are ready to look at the methods we're going to share step by step. So the first method we're going to share is to define sorting key, and the second one is sliding window, and the third one is binary search. So the plan here is that we first write the two solution formats for method 1, 2, and then we write the solution format for method 3. So actually, method 2 sheds some light on digesting method 3. So with that said, let's explain the ideas for each of the method. So first, let's look at the brute force way. So in some sense, brute force. So for method 1, so we define a sorting key tailored to the task, because we can define the k to be the distance of an item y to x. So in other words, we consider the absolute value. Then we do sort in a brute force way and get the k elements. So in this method, actually, this is roughly the time complexity. The reason is that we need to use this k to sort the original array. Let's assume its length is n. So we're going to use n log n time. And then we want to prepare the output. We need to sort the key items we located. So that is O k log k. So that's the time complexity. So here let's look at the first example. So here is the array, and k is 4. K is the number of elements to be returned. X is 3. So the distance to x is 2, 1, 0. 4 minus 3 is 1. 5 minus 3 is 2. Then after sort, the array is 3, because 3 has distance 0 to x. So 3, then 1. So we have 2 and 4, right? And then we have 1, 5, because 1, 5 have distance to 3, that is 2. right? So we have 3, 2, 4, 1, 5. So we need to return the first 4 elements, 3, 2, 4, 1. In sorted order, they are 1, 2, 3, 4, right? So this is the first method. So for the second method, actually we can use a sliding window. So we can imagine an auxiliary array of the same length with all elements being x. So for example, this is the array, and then this is the auxiliary array. So actually we can check all the length k segments. Then we compute the L1 distance of these segments correspondingly in array and aux. And then we find the first segment with minimal L1 distance. Why we find the first? So that is due to this assumption. So why could we examine all the length k segments? Because the array is originally sorted, right? So there are length array minus k plus 1 count of length k segments. So this is actually very simple to check. Then for example 1, so there are 2, right? This is 1, 2, 3, 4, and this is 2, 3, 4, 5. Then the L2 distance, so this part and this 4, 3, right? So we can compute 1 minus 3, 2 minus 3, 3 minus 3, and 4 minus 3. So sum is 4. Similarly, we can consider this segment of length 4. So the L1 distance is also 4. But this one is the first we meet. So we will return 1, 2, 3, 4. So this is for example 1. So actually for this, so we can make this implement this algorithm to use ON time. So this solution actually does not take into account that the array is sorted. So up to now, actually we explained the 2 methods for brute force sorting and sliding window. Let's first write the code for method 1, 2, methods 1, 2, and then we explain binary search, because we want to first share method 2 before we digest the binary search method. So with that said, let's first look at method 1. So method 1 is sort of brute force. However, the code is very short, sorting according to devised k function. So this actually is very routine. So I'm going to sort in place. So the k will be the lambda function, and then we're going to have y, the generic item, and then we consider the absolute value of y and x. So after sort, we're going to return the first k elements. So that is first k elements. However, this should be sorted. So we sorted this k elements. So this will give us the result. So now let's do a check. So this is for a special case. Now let's check the generic case. Yeah, it passes all the generic cases. So this way is sort of brute force. So now let's look at the second method. Let me copy this function signature, and then I'll change this one to be solution v1. So for this one, actually we do not need to have a auxiliary array, so we can do things on the air. So for this, I'm going to annotate it as sliding window. So for this, first I'll initialize L1 distance. So I'm going to have the first k elements, right? So that is item minus x for item in array, the first k element. So the first k element has index starting from 0 and ending at k minus 1, right? So then I'm going to record the start index, that is 0, for this first k item. And then we are going to do the for loop. So for I in range and k to m, right? Then what we are going to look at next, right? So first we want to update the L1 distance. So this is actually very simple. So it's the original L1 distance, because we consider a new item at index k. So at index I. So the increment part for the L1 distance should be array I minus x, but the decrement, because the very first atom should be discarded, so it's array I minus k, so minus x, right? And then we compare, right? If new L1 distance is less than L1 distance, so here it's not less or equal, right? Because if they are equal, we do not want to update the start index. So if it's strictly smaller than the previous L1 distance, so we are going to set the L1 distance to be the new L1 distance. And then we set the start to be I minus k plus 1. Notice that the starting index for next will be I minus k plus 1. So you can think of the first one have 0. So, right. So this is all the same. So after the for loop, we actually can locate the start index for the segment we want to return. So we just need to return array start and start plus k. So this gives us a length k segment. So with that done, so let's do a special case check first. So n is not defined, so let's change it to be array. So length array. Yeah, it passes the first test case. Now let's look at the generic case. Yeah, it passes all the cases. So now with this two methods presented, let's look at the third method. So first I'm going to copy the function signature, and I'm going to change this to be v2. So now let's go back to the analysis. So this actually is a little bit subtle, but it's still not that complex. So here, so we are going to use binary search. So this method actually makes use of the fact that the array is sorted ascendingly or sorted. So the intuition might be as follows. So we consider 3 items below. So actually we are using something called asymptotic analysis idea in mathematics, but that's not important. So first let's look at atom A. So if the given x is very small, for example, if x is less than or equal to the minimum of the array, in other words, the first atom, then we just need to return the first k elements in the array. So this is actually very easy to digest. Similarly for B, if the given x is very large, say x is greater than or equal to the max of the array, in other words, the last atom, then we just need to return the last k atoms in the array. So this is the two simple cases. And the third case is atom C. So what remains is the case that there are possibly this one. So there are some numbers is not larger than x, some smaller than x in the array. So in other words, this case. So the x is in between the minimum and maximum. So in this case, the length k segment to return would contain atoms that are smaller than x and also atoms that are larger than x, right? So now we're going to focus on atom C. So actually after the analysis, you will realize that the atom C covers the atoms A and B in code. So for atom C, we could use binary search. So we can search for the start index or end index for the desired length k segment we want to return. So here we shall have some feeding after digesting method 2. So assume the segment to return is this segment. They have a start and they have a length k. So our goal is to hope that, so the x, let's assume that x is larger than the smallest one in the segment and smaller than the largest one in the segment, as explained here, right? So we want this condition star hold, right? In other words, so we want this array start the distance from x, so that is x minus this one, is no larger than this one. So notice that start plus k is the next right index after this segment index, right? The segment ending at index start plus k minus 1. So, if star is validated, right? So it says that, so this array start is too small, right? Therefore, it has too large a distance from x. We should push the start to the right or move the segment to the right. So otherwise, we shall push the segment to as left as possible. So this actually explains the ingredient called search space shrinkage in binary search. So let's recall. So in typical binary search, there are two items that are, or two ingredients that are very important. First, search range. Second, search space shrinkage. Actually, it's also very important to define the order function, but we will not explain in that general case. So now let's maybe look at an example to digest. So here we have an array. This is one we cooked up so that we help understand the search space shrinkage or movement. So we have 1, 3, 5, 6, 7, 18. This number is very large, or you can put a very small number in front. So we get k equals 3. We want to return 3 items, and x is 8. So here n equals 6. That is length. So we can start from L equals 0. So this is the left index. So R is n minus k, that is 3, to do binary search. So this is going to be our search space, starting from 0 and ending at 3. So why the maximum of R is n minus k? Because we need to check the last length k segment, that is array n minus k and to n, right? So in other words, in this binary search, we're going to locate the starting index of the returned segment. So here, well, left is less than right. So here 0 less than 3. So we can compute the middle. So using segment increment, so that is L plus the distance integer division by 2. So that is 1, right? So in this case, we can check x minus this mid. This is 5, and array mid plus k. In other words, the next right index just after the segment. So that is array 4 minus 8. That's 0. X is too small. This array mid is too small, right? So we need to move to the right to minimize the L1 distance. So we set L to be mid plus 1. That is 2. So now let's look at one more step. So in this, now we have L equals 2 and R equals 3. So now if we use the increment to get the middle, that is L plus the delta divided by 2. That is 2, right? Because 3 minus 2 is 1. So 1 into the division by 2 is 0. So we get 2. Then we compute x minus middle. So that is 3. And then we compute the array mid plus k minus x. But here we have array 5. That is 18. That is so 18 minus 8 is 10. So it has too large contribution to L1 distance if you compare with the second method. So this is the fact. So we realize that array 5 is too large to include in the desired segment. So we set R equals 2 equals the mid. So now we have L and R both equal to 2. So we stop. Then the segment we are going to return is from L to L plus k minus 1, right? In other words, 5, 6, 7. So posteriorly speaking, so we know that we couldn't return the next segment, for example, 6, 7, 18. The reason is that 18 compared with 5, so it has too large a distance from the target x, that is 8. So we can also not return the previous segment, 3, 5, 6, because 3 minus 8, the absolute value is 5, is larger than the absolute value of 7 minus 1. So in other words, the difference is coming from including 3 or including 7. So we need to including 7, right? So that explains the 5, 6, 7. So actually in both the cases 1, 2, so the segment we examine has k-1 element in common, right? So that actually also explains the criterion star. So you see, right? So this is the first atom. The first atom in the segment. It's the right next element in the segment we examine. So with that said, so finally, so we could check actually star also covers the cases A and B. So therefore, we could write a very simple binary search solution. So here actually we do not need to check due to the format of star. Here I feel that the feeling or intuition might be important. So with that said, let's translate the analysis for the binary search to code. So here let me make some annotation. So here is binary search. So for doing binary search, here we do not need to write a Boolean function or order function. So I'm going to first find the search range or search space. So L and R will be 0 and the length of array minus k, right? And then we're going to do search space shrinkage. So for this, the condition is well L is less than R, and then we are going to compute the middle. So middle is nothing but L plus the delta R minus L into division by 2, and then we check the condition star above. So if X minus array mid, so it's large, then mid plus K minus X, right? So we should consider to include this element in the segment return, right? So we should move the left to the right. So we are going to set left to be mid plus 1. Otherwise, so this is smaller, so this is too large. We couldn't include this one. Then we are going to set the right to be mid. So after this while loop, as we analyzed using this example, so we should consider return array left. So here let me change this a little bit, left and right. So let's use LR just so that is as L plus K. So that's it for the solution. So let's do a special case check first. Yeah, it passes one example. Now let's do the generic case check. Yeah, it passes all the cases. So that's about it for this problem. So here let me give a quick summary to end this video. So in this video we shared 3 formats of solutions. So the first one is based on defining a device sorting key, right? So this is this piece of code is actually very simple and very short, so we can make it even to be one line, but that's not the point. And the second one, so because the original array is sorted, so we can use sliding window because the key items to return must be consecutive. So in this case, so we implemented a sliding window method and essentially using an auxiliary constant array, the constant to be the target X, right? So this is the second method. The third method actually is based on a slightly deeper analysis after the second sliding window method. So this is based on binary search. So this binary search is slightly different from the vanilla binary search, which is check membership, right? So here we check a segment, but this is the condition. So with that said, I guess that's all about it for this video. Thank you very much.